In earlier video, we introduced all of control instructions for PIC Micro. Let's go ahead and take this video and really kind of focus on the branch section. In later videos, we'll talk about call and go to. But for now, let's go ahead and focus on the branch instructions. The first thing is let's take a look at an example where we are able to implement a C code segment in assembly, just to get a sense of how typically that's done. So let's go ahead and say the C instruction, this example we want to work on, let's say it's a C code example segment where it says basically there's a variable A and it's 200, and let's say this variable A is a character or single byte, and then they'll do a while A is not equal to 0, do a certain thing. Let's say we just do A is equal to A minus 2, and that's all it does. Good, not a very exciting one, but it gives us kind of a sense of how a while loop, for example, could be implemented using branches. So the first thing we have to do, if we're going to do that, we have to allocate a memory location or an address called A. The way we do that, this is not an allocation, this is just the definition, so we don't have to say the location pointer all the time. So we're just going to say define A as 0x80. All we are doing, we said every time we say A in this assembly code, and this is the assembly code here, where what's above is the code, is the C code. So the first thing is we want to have a variable that points, and 80, if you recall, the data memory that is available to us, it starts at 80 and work its way up to 0xFF. So it's about 128 bytes, and each one of these has room for one character or 8 bits. So all we're saying is that we're gonna have A point to this location every time we want to use it, and we define a constant called A, so we don't have to remember that the location is 80. The next thing we're going to do is since the initialization is 200, we're going to do a move instruction, move literal word. This has to be literal because we are moving a constant, and the constant seems to be 200. 0x is hex. If you put a dot in here, that says this is decimal number. Great. But as you can look later on, you'll see that there isn't much we could potentially do with W register. So we gotta be able to move what is in W register to F, and that's the instruction that does that. Move WF does that. It takes whatever was in location 80, which at this point is 200, and move it, decimal 200, and move it into whatever was in W register, which is 200, and move it into location 80, which is basically, rather than me writing 80, because I define A to be 80, I can put that in there, and 200 gets moved into location 0x80. Great. Now, so we're going to have to give a label because we're going to loop, so we got to tell it where to loop back to. So we usually put a label here. Let's say for lack of creativity, we're going to copy W loop for while loop. And then in here, we can subtract, but subtract, as we talked about, we'll get to it, is a little tricky to use. This one is just decrementing by 2, so we're just going to do a decrement F twice. And that's some same as doing a set. And when we want to loop, as long as A is not equal to 0, so as we look at our branches, we notice there is one branch specifically suited for this, and that is branch not 0, and is capable of jumping 128-bit forward or backward. In this case, we just need to jump back a few bytes, And so that's a perfect instruction for us to use, branch not 0 W loop. Okay. Okay, that's great. Now, obvious next question may be, what is the binary? So somebody might ask us, what is the machine code for branch not 0 instruction? And in order for us to answer that question, they really have to kind of tell us what the address is. Although, since this is relative, the exact address doesn't necessarily make that much of a difference, but it's good to do that. And typically in assembly language, there's an instruction called org, and that instruction will tell you where you start your program. In this case, I'm going to say org 100, which means every instruction that follows, it's going to be starting at a 100 and work its way up. So if I come over here and put the address here, and to make our life simpler, let's just make the address hex, okay? So if the address, that means that because of this org instruction, this is an assembly directive, it's not an assembly opcode, it's not an instruction to microprocessor, it's the instruction to the assembler where to put the code. It's going to start at location 100. This is, we know this is 1 word or 2 byte, and if that would be 102, then there's another 2 byte, 104, there's another 2 byte, 106, and finally there is another 2 byte, 108, and if there was any instruction back here, it would be 108. Okay, so if they want the machine code for this, we have to do a few things. This is a branch not 0, so if it's branch not 0, we know that the opcode for branch not 0 is set right here, is 110001. The only thing we don't know is what is the value we need to put for n. And here's an equation. This is just an equation. You got to remember, this is how they use to calculate where they're going to jump. It's what they're going to do is they're going to say, okay, whatever the PC's program counter, the location in memory, program memory of an instruction, well, PC of the new, where you want the branch to jump to, that's called new. In our case, that would be 104. Is equal to PC, the location of the branch instruction. In our case, branch instruction sits at location 108, plus 2 plus 2n. Okay, so we use that to figure out what n. Remember, n is 2's complement when you enter it into the machine code. So how are we going to calculate that? Well, we're just going to look over here and see what these numbers are. PC new, or PC of where we want to jump to, the new PC after the branch is executed, wants to be 104. And remember, all these numbers are what? Hex. So all hex. Just to make sure, because I'm not going to, in the equation, I'm not going to put hex. It'll be too complicated to work with. And then it says, okay, what is the PC of the branch? PC of the branch is 108. Oops, I don't know how that H appeared. So equal to 108. Again, remember hex, plus 2 plus 2n. So at this one becomes a simple equation we need to solve. And so 108, that becomes 10a. We move it to the other side. And what we'll end up with is minus 6 is equal to 2n, a simple algebra. And then if you take that, that means n, oops, ugly looking n is equal to minus 3. Okay, remember, for this particular branch, n has to be 8-bit. So I have to write this n in 2's complement. So first, we're going to write n as a regular binary, minus 0, 0, 0, 0, 0, 0, 1, 1. That's just a simple binary. Then we're going to apply our 2's complement. If you remember what 2's complement, you either complement everything and add a 1 to it, or use the quick inspection, which says this number is actually equal to, keep the first one and complement everything else. So the branch, this particular branch instruction was going to be the opcode. The opcode for this was 11100001. So the branch instruction is going to be 110, and I already forgot what it was. 0, 0, 0, 1. I'm just reading it from the table, and then this becomes the end portion. This end portion that they say, and that's going to be 1, 1, 1, 1, 1, 1, 0, 1. So that is the machine code for this branch instruction. So that's the machine code for it. Also, although we typically again write it in hex, so this is going to be E1F, and that's CD. So that's how we write the machine code. That's great. So now let's do it. Let's do something we haven't done yet. Someone walks up to you and says that there is a machine code at location in memory. So let's even do it in a memory. This is another example. So we've got a program memory, and we looking at program memory location 0x290. So this is program memory, and we've got in this program memory, we've got 1A, and these are all, by the way, the content and everything is in hex, so probably should put 0x1A, and then we've got E3 as the upper byte. So let me rewrite. So this is location 290, this would be location 291, and our expectation is the next instruction is after that. They have asked us, you're looking in the memory, what is this instruction? What is the instruction? Okay. So you look at that and say, okay, so the instruction, if I write it out, it's going to be E3 1A, which is in hex. Let's go ahead and try to write this in binary. Binary is going to be 1110. And by the way, this is also sitting at location 290 for whatever it's worth. And then 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0. So that's the binary equivalent. Now we're going to go up to this one looking for an opcode that starts with 110. So we're going to go look up here. If it's not here, we got to go, oh, all of these guys are 110. And now we're going to look at the second byte to see if we can distinguish it. This is 1. So it's 110, 0, 0. Oops, that's the wrong instruction, sorry. So this is the instruction. So 1110, 0, 0, 1, 1. So we're going to look up here and see if we can find it. And we find 1 right here. As you can see, this opcode is exactly what we got. So that must be a branch no carry, unless we're making a mistake. So let me use a different color. So this is the opcode for branch no carry. Now the question is, where does this thing jump? Well, let's take a look at this. Branch no carry is 11000011. That looks E3. That's good. Oh, this 8-bit is an N. So what we're going to do is so N is right here. That's N. And remember, N is a 2's complement. But when we look at this, the most significant bit is positive. So this must be a positive number. And we look at that thing and we see that actually is a binary. Now in hex, if you write it in hex, N is equal to 1A. hex. Great. And it's a positive. So that basically tells us if you want to know where this thing jumps to, that means the PC, the new location it's jumping to, is equal to the location PC of the branch plus 2 plus n. Again, remember, we're doing all of this arithmetic in hex. Don't get confused and go to decimal. So PC new is going to be basically the 290 hex, the current location of the PC where the branch is, plus 2 plus 1a. Okay? So now if we add all of these together, 1, so a and 2, that is 10, 11, 12, so that will be a C. 1 and 9 gives us A, and 2 stays as 2. So this is the new location it jumps in. So if we wanted to write what code segment, what this branch is doing, this branch no carry is going to a location for loop. So this is right now at that location 290, but it's going to jump to a location loop down here, and this location for the loop is going to be 0x2ac, if I've done my math correctly. Okay, so let's take a minute and see what we have covered so far in this particular video. We started by giving an example. If you had a C segment that had a little while statement in it, how would you translate it into assembly? How it has to be translated to assembly to go forward. And since we've done machine code conversion for all the byte-oriented, bit-oriented, and all that, we focused on how do you do the machine code for the branch. And as you can see, there's a little bit of a twist, but you got to always remember this equation, and remember that n is 2's complement. Okay, so if it's a negative number, you have to convert it to 2's complement. And just as a last bit, we also took a little bit of a practice. If somebody gives us a code in memory, just looking in the memory, trying to figure out what instruction is being executed, we looked at that. We were able to go back to the table and look at E3 and figure out that's branch no carry right up here. And then the only thing we needed to do is figure out what n is. And again, we applied the same equation. PC of the new location we want to go is PC of branch plus 2 plus n. Did the calculation and figured out this is really what the branch is doing, is branch no carry to this location. This location is 2AC based on our calculation. That brings us to the end of this video.